Welcome to the Open Inventor 3D Software Development Toolkit for Oil and Gas Applications webinar. This is a short introduction to some of the powerful features Open Inventor provides for developing oil and gas applications. We do not intend to give a programming course, but rather demonstrate techniques which help meeting requirements that appear increasingly harder to reconcile. For example, how to manage larger and more complex 3D data with higher accuracy to reveal more prospects and optimize exploitation. Or how to deliver faster to the market working software solutions with cost-effective deployment. This webinar will show you how the Open Inventor Toolkit answers to some of those challenges. I will start with a brief overview of the elegant design of the Open Inventor API and take a glimpse into the toolkit's organization and architecture. I will then demonstrate how the API handles large oil and gas 3D data of different types with maintained interactivity, scalability, and very high quality rendering. Okay, let's get started learning about Open Inventor. Open Inventor is a leading 3D graphics development toolkit. An amazing diversity of 3D applications are built with Open Inventor, including geoscience applications, engineering design and simulation applications, medical applications, and virtual reality applications. Sometimes called 3D programming for human, Open Inventor can be seen as a productivity toolkit on top of OpenGL. It provides a SINGRAPH architecture, an optimized 3D engine, and an extensive set of built-in components to manipulate data using high-level concepts. Open Inventor is also a perfect solution for rapid application prototyping, both because you work at a higher level than OpenGL, and because many operations that 3D developers typically implement, like moving the camera and selecting objects, are already implemented for you. We've also built a number of extensions. They actually extend the set of objects, data types, and rendering techniques that are pre-built for you. VolumeViz is a full-featured toolkit for managing and visualizing volume data, whether it's a stack of images from microscopy, a CT scan, or a seismic survey. MeshViz adds support for managing and visualizing mesh data, whether it's a finite element analysis, computational fluid dynamics, or a petroleum reservoir. The hardcopy extension allows Open Inventor-based applications to output 3D graphics using the major vector formats, such as PDF 3D or PostScript. Let's talk about the concepts and architecture of the toolkit. Open Inventor is a C++ and Java and C# library. It's an object-oriented 3D toolkit built on top of OpenGL. Each object manages its own state, and for example, renders itself if it's a shape. The programmer doesn't have to take care about rendering calls. We build a tree of these objects called the SINGRAPH that describes what the 3D scene should look like. We call these objects nodes. You can see an example of a simple SINGRAPH here, and some examples of the kinds of nodes we'll use to build the SINGRAPH. In summary, your application will be responsible for defining the appearance and the meaning of the 3D objects in the scene. This is the most important part, where you use your domain-specific knowledge to create value for your customers. Open Inventor will be responsible for rendering an image of those objects and maximize performance and image quality, as well as ensure complex scenes are rendered correctly. Okay, let's start seeing some concrete usage of Open Inventor for visualizing a seismic survey. To quickly develop a test case rendering a seismic, we will use the Open Inventor VolumeViz extension. VolumeViz LDM enables rich interactive visualization of complex volume datasets. Different representations, including for example volume rendering, slicing, isosurface, and embedded 3D geometry, can be combined into a single Open Inventor-based application. The VolumeViz solution includes a hierarchical, multi-resolution large data manager, so-called LDM. This innovative technology allows rendering of extremely large datasets with reliable interactive navigation, even on relatively low-end machines such as laptops with 3D graphics. You can see an example here, how LDM manages the most relevant tiles of data in main memory and GPU memory for the current visualization. Yellow outlines represent mid to low resolution data in main memory. Dark outlines represent high resolution data in main memory, and green outlines are data in GPU memory. VolumeViz LDM is included in commercial applications today and has been stress tested on hundreds of gigabytes of data by key customers. It is designed to support up to multiple terabytes of data. Just so you get a glimpse of how amazingly easy it is to use Open Inventor, here is a very quick code example of a basic Hello Slice C++ program. To get the following picture on screen and start interacting with it, only a few steps are needed. First, the initialization of Open Inventor and its extension. Then the scene graph creation, or node instancing. Here, we create a volume data node pointing to the actual data on disk. VolumeViz includes a very advanced Segway reader for reading seismic survey out of the box. We also create a transfer function ensuring the data to color mapping, and finally the representation, here a slice. Next, the scene graph is assembled. And finally, an Open Inventor viewer is created pointing to the scene graph we've just created before entering an event loop. This is all it takes for getting an interactive 3D scene on screen. Now that we've seen a basic slice example, let's run another VolumeViz example with full volume rendering of the seismic. You can see the viewer's functionality, allowing rotating, panning, and zooming the camera. I take this opportunity to introduce another very powerful Open Inventor tool, the real-time scene graph editor called IVTune. IVTune is a built-in Open Inventor component and can be brought up at any time to help you debug your application, as well as modify and interact with the scene graph. You can see it as sort of a real-time 3D scene editor. Let's open it using the Shift F12 shortcut. You can see the application's scene graph here. Any node can be edited. Let's for example change the predefined color mapping of the seismic. Or edit the opacity curve. We could also customize the rendering by changing the volume rendering quality node. Let's turn on ambient occlusion and change the light direction. Nodes can also be deleted and added in the scene graph. Let's, for example, delete the volume render node and add new shapes. For example, orthoslice. Let's change the orientation of one of the slices and set a different slice number. We could also add a third slice with a different color mapping. Let's also change the orientation and slice number. Let's now start demoing how Open Inventor can interactively handle large oil and gas data through a set of advanced examples. Before I start, I would like to mention that all examples are run on a laptop. This is to prove the scalability of the solution. Open Inventor-based application will run on mostly any hardware with 3D graphics capability and will scale up with high-end machine. Okay, let's start with our first advanced example that shows the performance of Open Inventor picking through large data. The word picking in Open Inventor means selecting geometry by pointing. Any objects on screen can be picked, and a lot of detailed information about the selected shape is returned to the user. For example, if the face of a polygon is picked, Open Inventor will return information about the point picked within the face and all the face vertices. If a cell within a mesh is picked, you'll get information about it, and if a volume is picked, you'll get information about all the voxels intersected along the ray peak. This is what we are going to see here. This dataset has a dimension of roughly 1500 times 2200 times 1000 voxels, which makes a total of 3.3 billion voxels. Thanks to some very advanced algorithms, which are a combination of true geometric picking and shader-based technique, Open Inventor is able to pick any selected voxel instantly. No matter where I will pick, I will get the information. Now that I'm completely inside the data, let's try again. If I pick, I instantly get color, position in the data, position in space, and some additional information regarding the location of the voxel within the LDM structure. Now, if I zoom out, then pick, and without releasing, move the mouse, I will get information about any voxel the mouse is pointing over. This example gives a good idea of the kind of performance Open Inventor is capable of when facing large data. The next and last example with seismic data consists on literally sculpting the volume in real time. This kind of feature can, for example, be useful when wanting to extract information like horizon from the noisy dataset. Using volume viz, any volumetric data can be edited. Even a very specific voxel can be picked and removed from the data being sculpted. When you are done editing the volume, it is naturally possible to save the result as a new data. Any editing operation is possible using some advanced computed solid geometry. This technique uses Boolean operations of several geometries to create a new one, which will in turn be used by volume viz to clip the volume on screen. Let's have a look at it. As you see here in the test interface, there are three Boolean operation options. Let's skip the intersection and start sculpting. For example, I will only keep this part of the seismic. To draw the lasso on screen, I use some built-in Open Inventor tool. Once I release the mouse, the lasso is considered over, and Open Inventor then generates a 3D geometry as the extrusion of my lasso along the camera view. It then clips the volume against it, so we finally only see the volume I selected under my lasso. But I could also very well decide to remove part of the volume. Following the same technique, I switch to the subtraction option and select part of the volume I want to remove. Finally, I can use the union to add another part. And there is absolutely no limit to the number of combinations. Before I go on to the next demo, I also wanted to show that Open Inventor can clip in between surfaces or horizon. Now we will see the capabilities of Open Inventor Core to render large amount of points. With laser scan and geophysical data, the need for rendering large point cloud has become very common. Projects involving laser scan data range up to a few 100 million points. Open Inventor provides advanced technique for rendering huge point cloud while guaranteeing interactivity. Using shader, it can even render each point as individual sphere. Here is an example. So as you see here, there are millions of points. Now I am going to change the point size and render a sphere with maintained interactivity. The next part I am going to talk about is regarding reservoir modeling and how Open Inventor can handle the rendering and extraction of any type of mesh with its MeshFiz XLM extension. Large meshes and the associated data are a key challenge in application domains such as finite element analysis, computational fluid dynamics, and reservoir engineering. We address this challenge with the Open Inventor MeshFiz XLM extension. This is basically an advanced mesh API for visualizing any type of mesh with a structured topology or not, and any type of cell. In addition, the API presents a consistent model where everything is a mesh and cleanly separates extraction of derived meshes from visualization techniques. For example, an isosurface is not a visualization technique as in some API. An isosurface is a surface mesh extracted from a volume mesh. Contour lines are a set of line meshes extracted from a surface mesh, and so on. Let's have a look to some of the features with the visualization of a reservoir simulation. You can see here an example of a reservoir mesh with a lot of dead cells. This example shows a nice combination of different Open Inventor features. You can see annotations, text, and 3D gadgets like this compass or the axis. So the Mesh API allows to map any properties on the model. Currently we're seeing depths. And I am switching properties now. Let's get rid of the cell outlines. Many representations of the mesh are available. Here, this is the skin of the model. Let's switch to slicing. And add an isosurface. Let's change the ISO value now. Now let's go back to the full mesh rendering. MeshFiz XLM is also capable of filtering the mesh in real time, based on the current property values. Now that we've reviewed some of the XLM feature on a real dataset, I'd like to talk about its capacity of handling large meshes. MeshViz XLM has been specifically designed with that goal in mind, and it has been tested on pillar grids composed of more than 1 billion cells. Since I'm running all the demos on a laptop with limited main memory, I am going to show a synthetic pillar grid of 100 million cells and explain how MeshViz XLM is able to manage that kind of size. Once again, the key is the unique ability of Open Inventor to handle multi-resolution. Just like VolumeViz does, the MeshViz XLM design allows to dynamically change or downsample the mesh topology on the fly. If I show the extraction of a full resolution mesh slab on 100 million cells, as you see here, looking at the frame rate, this is rather difficult and not interactive. Now let's do the test on a lower resolution. This is now much better. But you could even handle that with automatic downsampling. This means that Open Inventor will use the full resolution mesh once it's available, and in the meantime use the lower res, hiding the extraction time from the user. Finally, I also wanted to mention that any rendering type can be mixed. So for example, you can mix a seismic with a mesh. The final part of this presentation will quickly highlight some Open Inventor core tools for handling well geometry and data around wells. Many tools are available for specifically rendering wells. They can be very useful for applications like well planning. See here 2 examples of well rendering using Open Inventor. Wells can also be handled with Open Inventor extensions. This slide shows an example of a mesh following a well trajectory. The mesh in this case can typically be mapped and filtered with borehole properties. Here is another example of a seismic data clipped around a well, for example, to visualize wellbore imaging. This is now the end of this webinar. I hope you found it informative. In this slide, you can see a few examples of the many oil and gas and geosciences applications based on our toolkit. You can also read some customer spotlight on our website. This short presentation just scratches the surface of the features provided by Open Inventor. There are a lot more that your application could benefit. Thank you for attending.